Okay, so optimization. I'm going to do things a little bit differently to start here. I'm going to talk about, I'm going to show you a game project I've been working on just to give you an example of something a little bit more than just a simple test to take a look at how the profiler works. So the reason behind looking at the profiler is that you can start to think about optimization early, but there's not much of a reason to. So, for instance, I could come in here and worry about the structure of my GUI or what code is running. But it turns out that I'm already getting 60 frames per second. So if I just look at the profiler here, or if I look at the stats, I can see that I'm getting upwards of a target frame rate. And there's a little bit of disagreement between these two, and that's fine. We'll kind of look at where they are differentiating, where they're making the estimations. Um, but overall, I'm above 60 frames per second. I'm happy, right? So there's not much of a reason for me to start optimizing anything here. There's some other things that I need to optimize elsewhere, and so we'll see what those look like in the profiler. But the main point is um, you can't really fix what you don't know is broken. And so the main point of optimization, or the main starting point for optimization, is testing. Okay, so the profiler is that, and thankfully Unity has a really nice profiler, which makes it very easy to kind of narrow these things down. And so we're going to spend a lot of time looking at the ways that we can use the profiler to analyze these, and then we'll also look at some tricks for optimization that are somewhat more specific to video games, and those ones we will actually come to some simplified tests or simplified scenarios that we're gonna build to. Um, so let's take a look at just what we're seeing right now with this GUI framework, and then we'll kind of look at the game loading up and see the other pieces. But while it's kind of simple right now, let's start there. So we see that we're kind of fixed at 60 frames per second, which tells us that there's probably something that is keeping us there, and there is. First off, I'm going to point out that we are in the editor, and so that is this others timer, right? So if I drop that, then we see that we really are closer to, oops, um, we are closer to the 100 frames per second or 60 frames per second or 80 frames per second that we're seeing up here. So that's one of the key differences is, this measure is trying to give us an indication of how fast we're going to run. The one down here is actually telling us that the editor is also taking up some time, and some of that comes from, say, this hierarchy view. So if I close that tab and I close this tab, we see that some of the stuff over here takes a little less time. But overall, you should just understand that while you're running inside the editor, things are going to run somewhat slower because of that. This view that we're looking at is what's known as a stacked graph. So the idea there is that as we add time from different components, they are stacking on top of each other for the total time. And so we can look at the breakdown, right? And we can also remove some of these things. So, you're already seeing me doing this with removing the other component, which is kind of related to the editor. So I remove that, and suddenly the graph does auto scale, but it puts us at around 100 FPS now, based on removing that. Or we can see, because of the spike, it scales back in, and that we're generally, over there, right? So we've seen that. Now let's look at this vsync thing, right? So that's the other piece that's taking up a lot of time. I remove that. Now we're kind of into just the rest, right? So I can see where my scripts are. So this is now down to most of what we care about, most of what we can control in Unity, right? The rest is kind of what Unity's doing. But we'll come back and look at that vsync because it actually turns out that we could turn that off and on. So there's my scripts, the blue segment there, and of course rendering is kind of the other big piece. And rendering is still a pretty big one, right? So there's really not a lot of scripting running, as you would hope in this case. And we can see some of this stuff. So if I click on this view, it's going to pause and throw me into the scene view. So I can click on 2D and I'll see that I'm still in the scene view, but it's really just a video of the GUI, right? A representation of the GUI. This graph below the CPU usage here is what's known as an icicle graph, because we see these little icicles down here um, that really represent the pieces of time, right? Um, so if we look at the whole loop here, we see there's some part that's the editor loop. It's taking up its time. Again, that's the hopefully most of the others piece, but there's probably a few things in there. And then this vsync is really the wait for target FPS. So it's maybe a combination of the vsync, which we talked about, where we are waiting on the render path. And again, I'm not going to bring up the slide in this case, but if you recall, the rasterization of the screen goes from the top left to the bottom right as it's drawing raster lines. And when it hits the bottom right, it has to sort of move the bar up to the upper left again, or move the little mechanism to start firing. And during that time, we can try to render some frames in the background, and that avoids screen splitting and all the issues that happen when we're writing to the frame buffer while the raster is happening. So by waiting for the target FPS, we're kind of actually giving it two things. One is we are doing the vsync, so we're saying, don't render faster than the monitor is going to, or wait for the vsync before you render a frame, which is going to kind of tie us to it. But it's actually, we could probably be running a little bit faster than that because we don't need to wait for anything. In this case, we have a target FPS set up in our player. Right, so I guess looking it up, there is a target FPS within Unity, and so we could be using that. We're not in this case, so I think this all is actually just the vsync in this case, but this would also tie to the target FPS as well, which is, let me show you here. So we have this target frame rate set. However, the code in this particular application is actually set to -1. At one point, I thought it is set differently, but it is only -1. Okay, so moving forward, we're seeing that most of our time. So when we're looking at a frame like this one, what we're seeing is this is our breakdown of a given frame, right? And so this is saying that we're taking a 16 millisecond frame. We start with frame 0 here. We can actually see some of the history over here, so we can see the previous frame over there and the next frame over there, and we're actually looking at this particular frame. So I can click on there and use the left and right arrow to step through the frames, but that's we don't care necessarily unless we want to look at one of these spikes. And in this case, we know that the spike is really just heavy on the editor time, right? So the editor time is what's kind of using up most of us, or most of our frame there, and so we won't worry about that. We'll just look at one of these sort of standard frames. Okay, so we're looking at the time, and then it's an icicle view where as we sort of stack things, as things are working in parallel, or functions are calling out to other functions, they are stacking downward, right? And so that lets us know how it breaks down. So wait for target FPS doesn't call anything else. It is its own function that is just doing its own thing. We can actually see where some of these other sort of breakdowns are, where they're happening. So we see things like the script behavior update, the mouse events, and so on. But this starts to give us some of the breakdown. This is not my favorite view because it's a little hard to work with. It's nice to see an overall of what's happening, but my preferred view is the hierarchy view because that is a little more clear, at least when you want to get to specific problems. And that's where we're going to kind of spend some time, because that's where we're going to look at the specific problem. So again, it breaks everything down as before. We see our wait for target FPS. As I highlight these, I can see where they're being used. So I see the camera render is there, the UGUI, the post update, all the kind of things we're looking at. Somewhere in here is our actual script code, but I think it's probably pretty low. Yeah, I guess I'm not going to be able to find it easily. So we'll come back. Oh, there it is actually. Okay, so this is the update loop for an actual behavior update. So this is calling all of the updates on all our code, and in this case I've got this class, maybe that's using some, or it's, I guess, using not insignificant time. I've got my config file. The post-process volume is doing some things. The music manager is trying to do some things. Really, nobody's taking significant amounts of time. But this is, the first pass, right? So we'll come back to this as we actually run the game. But we can look at the breakdown. So again, I'm going to leave it in this view. Let's go ahead and start the game up, and so we can see, some larger use cases, right? So here's a spike where we actually did see some pretty significant action happening, right? And so this is no longer, I'm going to drop the other code out so we can look at that, and actually I'm going to drop the vsync as well. And so now we can say, here is a real spike, right, of things happening. And when we come to the player loop, we can look at, where some of these things are. So let's take a look at some of those. See the breakdowns. Okay, I guess I can make my screen smaller. So again, the behavior update is where most of our code is, but let's see, there's probably a few things. Okay, so the one that's taking up the most time is this script delayed dynamic frame rate, right? And this is coroutine calls. So if you've not dealt with coroutines in Unity, they're a little bit like threads, but they're shared thread, or they're shared execution threads. So you have to explicitly yield out of your coroutine. If none of that makes any sense to you, don't worry about it. Coroutines are something you can use, but they're not necessary. You can do almost everything you need to do in the update loop, and you can even restructure update loops to act like coroutines anyway. It just depends on your use case. Sometimes coroutines can be a little bit invisible to see, but luckily we do get to see them in the profiler. Okay, so in this case, we've got this lobby player config start, right? So this was the thing that was setting up the fact that I joined the lobby on this game. And now we're looking at the breakdown. So let's go back and look at the timeline view just so we can see a slightly different timeline view. So this one's actually got, a pretty significant piece. So now our wait for target has used up less time because we're using up more of our whole frame rate. And so that's great. Just don't know why it runs at all, but I guess it does somewhat, probably because the graphics is still only using a certain subset of the time that it has allotted. So we can see that we've got this behavior update, we've got an event system update, and it's an object activate call. And in this case, it's the single player on enable which gets run that takes up a lot of time, right? So this is, I chose the single player view of my game, and so I enabled this single player script. And actually, we can go ahead and bring that up, and we'll look at this on enable and see what it does. It looks like most of the time here is in this instantiate, and that is often the case that instantiates are expensive, and so we'll come back and look at how we can save instantiates when we can. Right, so the on enable is instantiating the player prefab, or the lobby prefab, it's the lobby instance, and also enabling the battle menu, right? So if I come back and look at that, the battle menu is this whole piece over here with the lobby, and then the lobby instance is really the representation of my player within the lobby, the character I've got. And so if we come and look at the hierarchy view, which again is kind of the way I like to look at these things. So we do see, I'll show you, or let's look at this a little bit. So there's this self milliseconds and a total time. So this is the total time of this hierarchy call here, but because we're calling pieces below it, we need to look at that time. So there's really, if we look at the self time minus or subtracted from the total time, we should find the remaining time that's used within here, right? What that means is I'm using this activate awake recursively within game object. Again, this is internal to Unity and part of the instantiation. Takes 9 milliseconds. So those 9 milliseconds are subtracted from this total time, which says we've got another 6 milliseconds in child objects. So part of that is, half of that 6 milliseconds is this animator rebind, another half is the image on enable, and then a whole bunch of other calls that are happening to just set things up. And that's all really coming back to this activate on the battle menu. I'm trying to find, normally, the fact that this character is coming up also should take a lot of time, and I'm not seeing where that is. But let's step through and see where the remaining time taking up are. Okay, so the code, so we finally come to some code that I can speak to that isn't just Unity load up time, and that's this generate map. Okay, so here's an example of some code that I might care to look at in terms of optimizing, because this is one of mine. So this is the battle menu. This is the part where it's generating the map here. And if I load up that routine, right, so it's this under here, this start coroutine generate map. So here's an example of one of those coroutines. This, so this is a coroutine because I knew it was expensive when I first started it. I'm creating, doing some randomization, setting up a Mersenne twister, custom random number, doing some Perlin noise stuff, and then I have to go through the entire map and walk through it. And so this is one of those cases where it makes sense to coroutine it in this case because I kind of want to break up the work. So I do a little bit of work and I yield every 128 steps. This is 128 vertical steps as I'm constructing the map. I also have a few different other pieces instantiating here. Just skip past some of that because the details don't matter. It's also setting up where the players' start positions are, all that kind of fun stuff. And then I think there's another yield somewhere in here, and some expensive debug logs which go in there. So all told, somewhat of an expensive routine. I do break it up over a couple steps. So you see like step one. See, it's not called, I don't believe it's called in here. Yeah, it's not called yet by this time. The first step's there, 2 and 3. And I think it's only 2 steps because we actually wanted to see like 2 yields in there, or that first yield. And this is actually a pretty short graph. So it goes through yields about here and then finishes the rest of the chart and goes through because it's 192 tall. Okay. So the question is, do I want to optimize that? And the answer is no in this case, because I don't necessarily care. I'm kind of in the front end of the game. It's something that, when the player clicks the, I'm going to start single player, the fact that they have to wait for 100 milliseconds before the screen pops up is not too big a deal for me. I don't really care that it freezes slightly. I might, depending on which target platform I was hitting, if I was trying to get to the Xbox, they might give me a little bit of a hard time that I'm going above my 60 frames per second. And so what I could do is, unfortunately, this term is now global, but I'm going to flatten the curve, right? And so I've got this spike here. By yielding more frequently in my coroutine, I can push all of this time down along this x-axis, this direction, and keep it below 60 frames per second, keep it below my resource limit, but then it elongates it this direction. Okay, so a fair question leading in from that would be, what kind of time do I care about? And really, it's the time that the player is going to be playing the most, which is, maybe the core game loop in some sense, or it's really just when I get to the proper gameplay itself, when I'm actually doing things. Things like a pause menu, or even sometimes, you can, if the game itself is paused, if the core loop itself is paused, and you're doing things like inventory management, I might not care if that's as fast as it could be, unless inventory management is kind of a main piece that the character's going to do, and if it feels sluggish, that isn't great. But really, you can think of it, down to the player experience, and players are used to waiting at least a couple minutes to start the game up, and so the fact that it takes a few hundred milliseconds to get from one window to the next at the startup menu doesn't matter. If it was something that they were doing continually in the gameplay, that would be a big deal. So let's move on and let's take a look at some of the other timing things that are happening in here. So now I'm into a loading screen, and we see, there was a big spike already. So we saw the game actually froze for a minute, right? And we got that time. So this is a really big spike, right? However, it's an expected spike because we changed scenes. We started loading up a bunch of stuff. It's to be expected. But we can take a look at it and figure out what parts we might care are taking up time, and whether or not we want to optimize them to maybe make our load times a little bit faster. One argument to be made there is, as you're loading up a game, if you load it up faster, everybody gets to play faster, and so they actually, stay with your game a little closer. There's certainly many games that have very slow load times, especially between segments, and players hate that, right? So this is a way we could look at that. So I will probably not dive into this. I'm just going to note that this level loader is reading that map image that we saw earlier that we generated. So very similar thing, going through pixel by pixel and building up a map based on those pixels, right? So it's actually building real assets in those cases. So it has to do a lot of work. It also has to do some work in terms of setting up the graph and the ability to do navigation through there. So I'm not using Unity's nav mesh because that has to be pre-built. I'm just using a custom built nav mesh in this case, which is actually one of the places where some slowdowns happen. I do a whole bunch of calculations on top of that in terms of figuring out some stuff for the AI, where the AI is going to be able to place things, do connected components. We'll see that there's a bunch of islands, and so connected components tells me which of the islands are connected to each other. So therefore, before I even do a path query, I can find out if I can even reach that. And then the quad tree helps me do some queries as well. So there's a whole lot of setup that's happening right here. And then what we'll see is a lot of the rest of the setup is actually built into either updates over time, where I do almost like coroutines within the update as part of the like loading window update and things like that. Or else I have legitimate coroutines, and part of my landscape generation is a full threaded coroutine thing, which is doing a lot of work itself. So I guess some of that was actually happening in the background while I was paused because it really was threaded. So this whole island generation mechanism is like a dynamic voxel-based island tool called uterrains. And so that one's running in threads in the background doing all this stuff. You'll notice some weird stuff with the GUI here. That's because I'm paused, and so the GUI hasn't had a chance to update and push everything back to the corners where they need to go. Not too worried about that. But yeah, other than some startup time, most of the time there is actually bending the curve again to push out the processing that has to happen. So I can have a little bit, so rather than the game feeling frozen while it's trying to load, I can show a little loading bar, which is kind of a player experience thing, and allow things to be happening in the background. Okay. We are coming up to the end of talking about this, but let me go through a few more details here in terms of things taking up time. So we see another spike here in terms of the physics, which is kind of interesting. So let's take a look at the physics profiler and see what's going on there. So yeah, this case is probably due to the fact that I created a whole bunch of rigid bodies, and I create rigid bodies in this case to use for collision mechanisms, right? So I want to detect collisions versus triggers in a lot of cases, and so I have rigid bodies attached to things, but most of them are kinematic because this isn't really a physics game. It's more like an RTS or a MOBA type game. But I still use some of the physics bodies. Some of that could be optimized away. So I can see, a piece of code there, and that is something, I can take a look at to see, do I care that there's 600 and some odd 656 static colliders and 2 rigid bodies? Probably not, because once I've created them, for the most part, the static colliders aren't going to participate, and we see that further down here, that once they're all set up and ready, then they're kind of done. And so I don't necessarily care. I do have a few startup routines here that are kind of kicking off as the window was showing. And so that might be a place where I'd go back and look. This is part of the island generation routine, so that's still that piece. And some island loading. I think the actual startup is probably about here. Yeah. Okay, so this is the final piece. This is actually where I start showing everybody. This is one of those cases where this is loading up stuff off the disk to show assets, bring them in, and so there's not a lot to be done about that other than you try to make sure that that's before the game actually starts playing. And I think that's all I'll talk about here. So let's just look at the standard update loop and make sure that things like that feel pretty good. Got a scroll window, which ends up being problematic when you're trying to look at this stuff. Yeah, so we see that so technically, what I'm looking at here is not really running at 15 frames per second, right? So I do have to bring the vsync back in. I should probably bring the other back in just so I know what the editor is doing. But I could, in this case, expect that this is how a build would run. And we'll take a look at that. I'm going to actually make a build out of this and come back to like this view just to take a look at it. But yeah, so what I would hope is that my standard movement here, you'll see all kinds of interesting bugs that I need to work out. My standard movement should not be taking up a lot of time. We do see that my landscape rendering tool does spike occasionally, and so that's one that I will be looking at some point because it's an asset store build. Need to go branch out of that. But at least for the most part, some of the standard stuff is not taking up time, and so I'm going to build up a building so I can see and make sure that the pathfinding doesn't seem to have any big spikes. The fact that I'm bringing in a building doesn't have any spikes. All of these things I can verify, and I do see. Actually, I see. Here's a spike based on the fact that I was constructing something, but it's not a very big one compared with some of these other things. Oh, I do have, yeah, so there's a big one. So this spike here, this again is the fact that I am changing the structure and I'm doing that connected components thing. And so that one I expect to have some time spikes in there. I might try to flesh that out a little bit. I'm trying to make that as responsive as possible because that one is responsible, in this case, for the fact that I can see this icon change to show that I can walk here, and I see that it doesn't show an icon over here. So it knows that I can't walk to any of these islands yet because they don't have connections to them, but it does see that I can walk here. So if I were to click over here, it does nothing. It doesn't even bother trying to pathfind. So I'm okay with spending some time on the Connected Components Manager in order to make sure that I can run fast with my mouse and things like that. I also have to make sure that this thing comes in pretty quick in terms of, see all kinds of bugs with this version, in terms of having it, rather than having it do a coroutine update, I try to make it update as quickly as possible and maybe spike up to down to 30 frames per second from 60 in order to get that update to happen as quickly as possible. Okay, so I decided to cheat a little bit and just restart. So I was running into some issues with the last little build. But let's take a look and make sure that there doesn't seem to be anything too outlandish in terms of time here, right? So yeah, we are seeing spikes, and those are likely due to the orchestra setting up the island generation. I'm not going to worry about that right now. But what you'll notice is because I built these bridges, and you didn't get to see that, but there wasn't a big spike as I attached these things, which you'll have to trust me in this case because I skipped forward. But the purpose of say, the Connected Component Manager is now these components are connected and I can do a quick look, right? So this is mostly to point out that there are computer science type algorithms that you can use to speed things up. And it's certainly worth understanding those, but that is kind of a degree in itself. So those of you who are computer scientists, of course, should be learning about big O notation and optimization and various algorithms and data structures. And that's a little bit beyond the scope of this discussion. But it's something that is worth being aware of, that sometimes you can speed things up that way by using some algorithms that exist, especially to save time on your AI or to save queries on your AI, like quad trees and all that kind of stuff. Here's one last thing I was going to show you with this, and that is the ability to debug a build or profile build. And so to do that, I'm going to click the development build and auto connect profiler there. I don't think it actually auto connects when I start up, but we'll see what happens. And I'll do build and run. Okay, so here we see the build, and what you can see in the background there is the profiler is running. So it does usually auto connect correctly. Luckily, you can usually, if it doesn't auto connect for whatever reason, and you're not seeing the build come through, then you can still click and find it over here. So now I'm going to turn on the others and the vsync because I kind of want to look at these things. It does become a problem. It's actually harder to debug in some cases because you actually can't pause your game, right? So the game is continuing to go, and looks like I've got some AI bugs happening. And while it's going, it's running some profiler data, right? But you can kind of get a sense for what's happening in the background as you're doing it, um, and see, some of your pieces. You can also pre-click, so you see the highlighted piece there. If I have something in particular I'm worried about, and so I can look at those and highlight them, and then see them highlighted in the view here as it's running through, and I can look for spikes in those cases. So it's easy to get a sense for things. It's a little harder to actually look through and be able to analyze it without pausing the game or pausing the game loop. I could, I believe, build in a pause here, but I'm not going to in this case. Uh, yeah. So anyway, so it is possible to come back in and look at the profiler for a particular build. And in this case, now that I've killed it, I can actually go in and look at each of these pieces and at least see the last couple seconds of the game. So we see, things like the others actually has a much less, uh, a smaller impact. The VSync is pretty much not there at all. So a lot of things that we were seeing from the editor don't come into play, and we are seeing sort of a realistic figure for how expensive the game is, or how expensive certain updates are. So let's take a look at a simpler example. This is essentially all I've got is this spawner here, which is spawning a whole bunch of objects. We're going to kind of look at a few sort of easy cases where things break down a little bit, and then how we might address some of those. So what's happening is we are giving it a spawn rate, so number of objects we want to spawn per second, and then we are spawning those. So every time we've got at least more than one to spawn, we'll start spawning. And this can handle however many we end up wanting to do. I do destroy them when they drop below 100 in the Y position. So they get destroyed, they get instantiated here, and it's just a big loop of sending them in. So there's a sort of a maximum here, and we'll see where that's useful in a minute, because we might expect that, in general, we don't have our objects grow to infinite numbers, but they do grow quite large, and even with the large numbers, then we run into some issues. So let's take a look at what that looks like. I've got a few sort of very obvious things that I did wrong in some sense to break this. And we'll look at those and see how they impact, especially when you're looking at 10,000 objects. So, I mean, the first thing that's not necessarily wrong, they're all kind of spawning on top of each other, and the physics is just going wild, right? But that's okay. I just want to show a whole lot of crazy interactions happening at all times, causing these kinds of problems to go. So we see that, and we start to slow down significantly, right? So we see a huge jump in our physics over here. And there's a couple things that are doing that. One is that my sphere so this is the sphere that I'm creating over and over, is not actually a sphere. It's an ovoid, or an oval shape, because I did a non-uniform scale. And so non-uniform scale can sometimes cause massive problems. So what you want to do is, if you can, change your scaling in your modeling program, in whatever way you're trying to scale things, and then make it so that your scale is only 1 by 1 by 1. Now, that probably doesn't matter as much if it's not a rigid body or not doing a static collider. And then ProBuilder does some special things to make sure that your scale remains the same while still being able to sort of scale and stretch objects anyway. So ProBuilder is pretty good in that sense. But if you were trying to gray box your level and you ended up doing non-uniform scales, that's probably not a problem. And it's actually less of a problem in Unreal, I think, because they manage it a little better, or convert it back to a sort of uniform scale, even though you're modifying the model. But again, it's not something that you need to worry about unless you're profiling it and seeing a problem. And so in this case, we're profiling it, we're seeing a problem. We don't know necessarily that our problem is this, but that's why I'm telling you it, because now it becomes something that you can go look for. Am I having a lot of physical issues, or does it seem like there's a lot of extra processing Unity is doing with my objects? Maybe I have a non-uniform scale and that's causing me a problem. So that's one of the places to look. So let's see what happens if I just switch it from, I had 3, 2, 1 here, so arbitrary numbers. Let me see what happens if I switch it back in terms of scale. So we see it go just off the charts here. And And now we see it's a little more regular. The collisions are obviously, a little more uniform as well. We start to grow big, but we kind of cap out at, say, 15 frames per second here. Okay. So, and now we're at kind of a maximum. So we can see the number of batches here is around 7,500. So that's about what we're actually looking at, is between 7,500 and 8,000 objects on the screen. Again, because some of them are getting deleted. So we kind of know we have sort of this somewhat arbitrary cap. We don't know necessarily maybe what the cap is. We got some weird gameplay elements, generating these spheres and then deleting the spheres when they get too low. But thankfully, it kind of caps itself out. This is something you might want to keep in mind for your games, to make sure if you're allowing users to, or game players to, create things, that maybe give them a resource limit so they can't create infinite numbers of things, right? Unless you're trying to make a Minecraft game, and then maybe you allow them to do infinite numbers, but probably they have to mine some things in order to get the materials to then create the new thing, right? So lots of games do resource limits, and not necessarily because it's optimization, but it's certainly a good idea to make sure that there's a resource limit to force the player not to be able to create infinite numbers or something. And yet sometimes it happens. The game I showed you earlier, the bridges are actually not necessarily resource limited except for over time, so you can technically create thousands of them, or yeah, probably only tens of thousands, maybe at the most. Okay, so the next piece of optimization is that I am using a convex mesh collider. So if I did a non-convex mesh collider, I wouldn't have any physical interaction. So if I turn this off, there won't be physics interaction. And you'll see, in fact, we'll take a look at that. Pretty much the balls are just going to sort of drop through the form and disappear. We'll actually have many fewer too, right? Because they're really going to drop straight down into the floor or through the floor and then disappear right away. So we don't get nearly the same number as we had before. So that's not interesting because we maybe want the physical interaction. The problem is the mesh collider was taking us up to around 15 frames per second or 66 milliseconds. So if I remove that, then and I go back to a standard sphere collider because I'm dealing with spheres, then we're okay. And maybe, I might actually be able to get away with like the non-uniform scale with this, but let's take a look at what this looks like in terms of time. So we'll see it growing again. However, by the time we hit our sort of customary 75 to 88,000, we're a little bit lower, right? So it's not significant, but it drops a little bit below. So we were a little bit above. Actually, we're going kind of above. But we're in sort of two places, I guess. We're kind of down here, we're kind of up here. I'm not sure, some of this might be caching too. But we're a little better, right? So really, I would say the main problem here is that we're probably using physics when we don't really need to. It might depend, so we might actually want all of these collisions to be happening, but maybe what we really want is just a fountain of these ball actors, flying out or whatever. A little bit like we saw with the collisions, but that they'll only collide with the plane or something like that. So I'm going to modify the code and create a new script on top of the sphere here that then only really collides with the plane on the bottom. Okay, so I made a few changes here. I will show you what they look like first, and then you can see what we're seeing after they start. Okay, so notice that the balls aren't really flying up. There's not really collision. They're just kind of bouncing along the ground here with some sort of weird elasticity, and we can take a look at that. We also see that our numbers are growing substantially higher than like 10,000, right? Now, they're growing substantially higher than 10,000, and yet we're kind of doing okay, right? We're not doing terribly here. And this is going to give us a place to start looking at some other things, such as like what we can do about the scripting, or at least how we can measure the scripting a little better, as well as what we can do about the rendering taking up a lot of time, right? So if we look at this, we see that the render time, and we can kind of capture this as, what is happening inside the GPU in this case. Sorry, I'm noticing some strange looking images there. It's partially because I did semi-transparency here, and actually I did that intentionally so that we can get a higher render time. And we'll see that in a minute. And then our script is actually taking a long time too, right? So just to look at it, I've got this new script called ball control, which here's a case where we can see that it's being updated 25,000 times. and that takes a long time. But each individual call, if we were to look at 25,000 times, not actually that big, right? This is milliseconds, so this is already 1,000th of a second. Our ball control update is probably in the nanoseconds range. And so that's totally good. What we worry about maybe here is that we really don't want more than a certain high number, right? And so we'll take a look at maybe that. The other thing here is that we do have a lot of instantiate calls, which are happening, and these are increasing our memory every time, right? So over here, we have a pretty big spike of memory going on as things are increasing. And so that's another place where we can start to look at, what is happening. The ball control script, oops, I may have forgotten to actually save that. I think I did. Okay. Well, we'll see how different that is. So the ball control script is doing the gravity velocity calculation. There's no collision now, so none of those balls are colliding with each other. Which, of course, if we wanted that, then we might need to go back and look at having the physics come back in and control the numbers that we're using. But that's going to be a big portion of our game. So that's actually starting to become a design decision at that point as to how much we really care about having this particular whatever effect we're doing here. So we have a simplified version of physics happening here. And we also have this sort of simple, perfect elastic response, right? So if we're below the line, then we get a velocity that is exactly however far below the line we are. In some cases, we actually get spawned below the line because our spawner takes the full sphere around 0, 0, 0, and some of our balls will be spawned below and then get shot up in that way, as well as they do get a velocity that's added to them at the start by the spawner. So the spawner actually picks a velocity which is always greater than 0 to spawn them off. Okay, so let's take a look at a couple things here. One is I would like to see how many per frame objects I'm destroying, and then I also kind of look at how big is this section of code right here. So Unity has this extra feature that we can use called the profiling module, and we will use that in order to add some extra profiling here. So I'm going to say begin sample. And what this says is I want my own custom profiler event, right? So this tells me that I can, that when I'm looking at the profiler, I'm not just going to see updates, but I'm also going to see the new capability, the new line item sphere removal and sphere addition. In fact, I'm going to go one step further here and actually say this is my spawner. Now technically I can track that down because I will still see that these are sub pieces of the spawner update, but this is a little bit extra information that I can use to peek at it when it's running. So let's rerun and let's take a look at how we can tell how much time we're spending on each of those pieces. Whoops, I forgot I left this disabled. Let me just go ahead and disable it to start. Alright, so we'll wait until we get a few objects spawned in there after a few seconds and take a look at our timer and see how long they're taking. Alright, let's click on current. Let's pause for a second. So we see this new addition. So far our balls haven't started being destroyed yet. We're just getting spheres added every frame. But we can see at each frame it's getting called 110 times, and for 110 objects we're getting 12 kilobytes per object. And that gives us a sense for how much money or how much memory is being added as we go. So let's go until we see them hit the edge here and see how long it takes before they start to die off. Oh, okay, they're dying off a bit earlier. This is good. I had forgot that I set the size to 100 at one point, and now I set it to a magnitude of 10. Just to be clear, let's go take a look at that code. So that is if our object's positional magnitude is greater than 10, meaning it is essentially 10 away from 0. Remember that position is a vector from 0, so if we take the magnitude of our position, it's how far are we away from the 0 point, which is where we got spawned in the first place. If we're greater than 10 meters away from that, then we delete ourselves. So now we should be seeing some deletions happening. Yeah, probably somewhere about the time it flatlines there, right? So we see the curve grow with just updates, and then we can see the removals start to pop in. So there's a couple tricks that I wanted to show you with that are somewhat specific to games in this case, because we know that we have an update loop and we know that we're going to create and destroy a lot of instances. So one of them is what I refer to as, say, update level of detail. That's where we start scaling when things are updating. So I'm doing that now. I'm allowing the number of balls to increase to very large sizes, large counts. But what I have in my ball control script is this minor change where I say I pick a next update time somewhere between 0 and 1, so that's the value here. And then at any given moment, I'm going to not update if I'm not within that time, and then I'm also going to increment that time by 0.05. Okay. So everybody's going to pick some time within the next second that they'll update. It's probably not the best version. I might actually want to do something like 0.05 times random value here, say. But that's fine. Within the first second, they'll start updating, and that's why you see them kind of stuck there for a minute, or literally a second. And then they start moving. But the idea is that rather than having everybody update or do this full check here every time, and especially, this one is not very expensive. We already kind of looked at that. It's pretty cheap. Instead of having them update every time, we can go through and just say, well, let's, pick, just return right away if you're within the not your window, and then otherwise you can update and do some complicated math, and then you stop updating. So you'll notice that it's not too bad. Basically, all the balls are updating at 20 frames per second, regardless of what our frame rate is. And of course, in the cases where we're below that 20 frames per second, now many more of the balls are updating. But if we go and look in here and see, so I put in that extra profiler in here for ball update. If we go and look at that, we see that at no point do all of all our balls updating at once, right? In fact, it's some fraction. It's actually fairly large fraction. It's not a subfraction, especially at this big point. Because I also set up a max count, so I don't allow the ball count to go above 25,000. So of course our batch count is about 4 times that, partially due to some of the things that are going on there. Not a direct tie to number of objects, not a direct tie to the draw calls, but probably closer to the draw calls in the end. But anyway, so that's one method of doing that. So you don't update every time, especially so Unity's going to go through its update loop every single time. It's going to walk through every object, and so there are other ways to actually disable objects and take them out of Unity's update loop to simplify that. I didn't do that here. I let it still run its update, but I saved the more complex code, which again in this case is not really that complex, to only update within a window. Okay, so that's one of the tricks. So you just try to make sure that everybody's kind of updating not all at once. This is especially useful for AI, which does some really complicated stuff. And so rather than having the AI do, so all, let's say you have several AIs, 8 to 10, that are all doing some complicated math or complicated algorithms, you might actually say, well, let's let AI number 1 go for the first, 0.2 seconds or 0.1 second or whatever, and then the next one go for the next 0.1 second. And so over the course of 1 second, all the AIs are updating. So all 10 AIs are doing a 0.1 second update. But they can actually spend 100 milliseconds doing that update, as long as you set up coroutines and whatnot, because they are working on exclusively within that window. So again, this is just kind of level of detail or windowing or number of different terms there. But because we've got this update loop that is continuing over time, it's very similar to many other things that we've kind of looked at. We are essentially just spreading the time across the window here, especially because for certain things the player's not going to notice, and so we can kind of get a lot more affordance in there. The other thing I'm doing is what's known as object pooling. So again, we didn't really notice a huge cost to the update here, but I don't like that it's allocating every frame, right? And so, and we can actually look at this because we'll see it down here. Let's see. I don't know that we got to the maximum, but we can probably look at what is happening. Yeah, so we can see, I think, both instantiated and unpooled. So I have two different calls. One is down here. We'll just look at this. So if we've got something in the pool, we'll just unpool it, and rather than instantiate it, we activate it, and then we set its transform and rotation this way. So we sort of just reinitialize the object back at the origin. For more complicated objects, this can be complicated. So the pooling is not unchallenging. But I say I've unpooled something when I'm pulling it off the pool. Otherwise, I have to instantiate it. So we can look at our counts, and we see that, at this point, we're still creating a lot of objects. And we're only unpooling 20 because we only pooled another 10 or 20 or whatever at the start of the instance. So we'll try to, unpool as many as we can, especially those that got deleted. So pretty much what's happening is really we're deleting 19 and then we're immediately reusing those 19, which is great because it's an order of magnitude less. So there is an order of magnitude fewer calls, but if you look at the timing, it's still much smaller, really. So that's great. So that's a savings in both in time and in memory because you'll also see that we're allocating 16 kilobytes up here for all of the objects that we're instantiating. We're allocating 0 bytes here. So even though we are creating new objects supposedly, we're not actually creating new memory. And so pooling is a incredibly useful tool when you're doing games simply because you are constantly creating and destroying things. You're constantly creating like bullets or missiles or little VFX like blood splashes or bomb attacks or whatever, and then you're destroying them shortly after, right? And so, but you're constantly reusing these kinds of things, and so having a pool means that you maybe create a few of them up front with a real instantiate, and then later on, all you're doing is just reactivating and then re-deactivating those objects over and over again and treating them as though they're new objects, but really pulling them off of your pool and leaving them in memory. You do use more memory. You keep the memory active at all times because you never get rid of those objects. You never actually destroy them and save the memory back. But once you know kind of and this goes back to where we were talking about, there's sort of this gameplay and resource limit that tells us what our maximum is. If we know what our maximum number of objects are, and we know how much memory they use, then we kind of don't mind that we're leaving some in the pool because our pool is sort of just set to whatever the maximum size is, or between the active instances and the pool, we have our total set of objects that we're ever going to have. And in either case, both are sitting in memory, and our total usage is just what our total maximum usage is. So our game just kind of always uses the maximum amount of memory, but it does so very efficiently by reusing that memory. So hopefully that was all clear. Again, I'll kind of bring up this code one more time so you can kind of take a look. We do, rather than destroy here, if I'm going to use the pool, rather than destroying anything, I just add it to my pool and remove it from my instances, right? Well, I always remove it from my instance set if I'm destroying it. But otherwise, if I have something in my pool, then I use that instead of destroying the object, or I mean, instead of creating a new object down here. And I did add this extra code here to finally put a max count to make sure that didn't get out of proportion. But of course, it's still slow. It still ends up getting much slower than we can deal with. So our max count is maybe too high, regardless. But that's okay because what we want to do is look at like how bad things can get and deal with it at that level. And then of course we just make sure it doesn't get that bad. So moving on, we'll talk about some other optimization that we can do. So as I have probably mentioned before in class at some point, we have 70,000 batches, which is around 70,000 draw calls. Actually, there's not a direct correspondence between batching and draw calls. In fact, I think there might be more draw calls than batches, like a multiply factor, depending on if we have shadows and things like that. And so that's going to have an impact because when I talked about it, we wanted something like 10,000, right? And so 10,000 is maybe somewhere back here. We might even be able to see by looking at, say, yeah, somewhere in here we're doing 9,000 updates versus 19,000 updates or whatever. So yeah, so somewhere in here we're at, say, 10,000 draw calls, and yeah, that's slow. But okay, we can kind of deal with it, maybe with it, depending on what we're trying to do with the game. Um, but that's maybe a target to shoot for, maybe even 1,000 draw calls, right? So we're well above that when we're in the 50,000 range here. So that's a huge problem. So let's take a look at one of the magic things that Unity has that lets us reduce draw calls. And that is the GPU instancing flag right here. So what this does is when we want to have these draws happen, um, then we have to say, load up this sphere, load up its position, here's all of its data for rendering it, and then run that. What we could do instead is put all of the positions and rotations into a vertex buffer object and have this one sphere be sent once the entire time. So all of the sphere, all of its textures, everything like that is sent once, and we say, here's 10,000. Here's an array of like 10,000 object or 10,000 variables, the vector and the rotations for the 10,000 iterations I want you to render. Now inside the GPU, when it's rendering those, it's having to actually iterate through many instances, right? So many triangles. Sometimes, depending on the level of the shader support, you just send the ball once, and that goes in, and then you render all of those positions. The other option is that you have to send copies of the ball in the vertex array. So you multiply your vertex array by tens of thousands and send that along. It really depends on what kind of support you have within the shader system. So I don't know necessarily what Unity's using underneath. I think it's probably actually using an advanced shader setup because I am on DirectX, and I think OpenGL doesn't have the support for that. But it supports kind of both. I'm not going to try to show that, but you can test this out on, say, a Mac or Linux version of Unity if you're really interested and see whether or not it works for you. So by doing this, what it's going to do is send all of these instances, as many as it can, in at one draw call and tell the GPU with some complex stuff inside your code, in the shader code, that we don't really need to see because, again, we're kind of just modifying our shader. Our shader is just this test custom shader that I'm playing with that does this, right? That just does this strict color, sets the or the metalness and smoothness. This is actually one of the simpler shaders. So going back to the shader lecture, this is one of the simpler things we could do, right? Basically the default shader, but it's here so that I can actually play around with it. So I took the alpha out because alpha ends up screwing around with the instancing. So I just took that out, and you might find other reasons that the instancing doesn't work. But anyway, let's take a look at what happens when we do this. So we see a very large green block right here from our previous run. As we wait for the batches to go, we start noticing that the batches are not actually crawling all that high, and instead what we see is saved by batch is what's actually kind of crawling up. So this is the number of instances we're actually trying to render. This is the number of batches that we're actually rendering. Okay. So what you can see here is that we are now able to see the top of our render peak. Oh, maybe we're kind of losing it a little bit, but it is taking a lot longer to hit that top peak. Okay. And that's because we are now batching and essentially letting the GPU do its job correctly, which is not spend a lot of time talking to it and spend all the time letting it just render the triangles. All right, it's still slow, it's still up here, but we're now, our render thread went from, say, 90 milliseconds to much less, 35. Okay, batching is a great thing. Unfortunately, there are a lot of restrictions on when you can batch. You can't batch a skinned mesh renderer. Semi-transparent objects often cause problems with that because they have to be rendered in a certain order, and so you start to cause problems with allowing the batching to even work. The objects can't be, they all have to share the same material because changing the material actually changes the batch. So in this case, they all have to be this material that we're instancing, another material would use a different instance. And there's a variety of reasons that you can't batch. Um, but there's a number of cases where this works pretty great. The other thing to consider is what's known as static batching, and that's really where we end up baking everything into a single mesh, right? And so Unity can support that to some degree if you start marking objects static in your level. What I would recommend is the better control for that is actually to go into Maya, and when you have started creating your level in something like Maya, create large, however you put it together, however you plug these components together, fuse them into a single object in the end, right? So a single object from being exported from Maya, being imported into Unity with a very large number of triangles that spans your entire level, a huge object, but you get a single draw call for that. The downside is, of course, that it is no longer going to be clipped correctly, because if it's a huge object that spans your whole level, it's probably always in screen in some piece. But that kind of doesn't matter too much anymore, and your mileage may vary depending on what you're doing, but that's something to look at. Because we can render so many triangles in the system, so we're doing 50 million triangles here without really breaking a sweat. Well, we're breaking a little bit of sweat, but still we're getting up to 50 million triangles per second, or per frame, which is great, and still kind of interactive. So it's not really an issue of you need to clip out those objects. You really need to reduce your draw calls. That's maybe the main point. If you keep that number down, you can start to do an amazing number of things. Now, there is still some time left in the renderer, so let's take a look at some additional ways that we can play around with that. All right, let's look at a few new optimizations. So first off, what I've done here is said it's changed from the standard output to Lambert. Really, we'll look at this in a little bit, where we have some semi-transparent standard shader and a whole lot of objects looking through that are doing nothing. But I want to show you this first. So we get some speed up here, but if we go in and we turn out the light, then we'll notice even more speed up, right? So the lights are kind of multiplying our batch. We still have some non-trivial amount of lighting happening in terms of the gradient of the sky is being reflected on the object, which is great. It looks nice. It's a sort of coming from this ambient occlusion parameter here, I mean the ambient lighting mode here, so saying use this lighting mode from real-time lighting. Oops, didn't mean to change that. We could pick slightly more simple versions of that, but it actually doesn't change much in this case, because most of the work that's happening here is let's go back to that and view baked. Anyway, so there's not a huge difference really, because it's the dynamic lighting that's costing the most, right? So we take the number of batches that we have, and then we have to multiply it by the light, and everybody has to be rendered. The simpler the lighting, the better. Lambert's probably as simple as we can get. We could try to go simpler and just return the output color, but it doesn't actually make a huge difference in this case. So the takeaway here is that although we can get some pretty advanced lighting effects, often you only need those on the things that are close up, and so we would use level of detail to pick between those. So I'm not going to go through the level of detail system that Unity has. It's pretty straightforward. It is there you create an LOD group, and then you can add different models to each LOD group, and then you specify the distances from the camera to each one. And so cold here is that object's not going to be rendered, and then we have different versions of this, and I will let you look up on your own time what those are. You essentially create children objects with different levels of shader, different levels of material, different levels of polygon counts as well, if you really want to. That might not matter as much as getting a less complex shader. But then what that does is helps you manage that things that are close to the screen use the complex shader, and then things that are far away from the screen use a less complex shader, so that you can render more of them when they're far away from the screen. And of course, if they're far away from the screen or from your view, then you are gonna see more of them. Think trees in a forest, that kind of thing. You actually probably want to use a lot of LOD there. So if we take the concept of level of detail to its most extreme, we wind up with what is known as billboarding, which is essentially just a flat image that has all of the detail that we might care to. So one of the more obvious examples of that you'll see in games and otherwise is the skybox. So behind me, I've put in a skybox, which is a bunch of images from all the various angles that we would look at, except maybe downward because we don't necessarily care about the down angle that much. We can look up as well. Oops, tilt, but or not pivot tilt. And so doing so, it appears that we have a whole lot of detail in this scene, but of course this is just a panoramic view from some hilltop somewhere, which is cool. And we capture a lot of detail and a huge depth of rendering, but it's all just an image, right? So the timing is just an image. A different way to look at that is what's known as billboard asset. So Unity has support for that. I'm not going to try to spend a lot of time talking about it. It's usually trees because trees are a popular one to billboard. You get a whole forest. You usually want to try to simplify that as much as possible and yet still be able to render a whole forest, which is great. Of course, we can render a forest out here with this version. But if you look at this billboard asset instruction set, then you can see that we could also, from a given, in this case, a tree asset, very complex tree, we can get a few different angles. And what we do in that case is just draw the flat view, which is a few triangles here. You see it's like 4 triangles from each direction that the tree is in. And then if we're far enough away, that's more than enough to get the idea that there's a tree out there. We don't need the special lighting. We could put some depth or some bump mapping into that tree and things like that. I don't know whether or not that's actually supported. I think it might be, depending on what you put into your renderer or into your material in your billboard shader. But in the end, you're far enough away at this point that all you really care about is you're getting kind of the gist of the tree. And then at some point, as you get closer, it'll change from the billboard renderer to a full renderer. And of course, the LD group will support all that.